Okay, so this video is on section 2.5, complex zeros, in the fundamental theorem of algebra. So in section 2.4, we were factoring polynomial functions over the real numbers and finding the real zeros of a polynomial. And remember, the real zeros ended up corresponding to x-intercepts for the graphs of those polynomial functions. So now we're going to think about polynomial functions in the complex number system. And remember, we reviewed complex numbers at the beginning of the year. All complex numbers can be written in the form of a plus bi. Okay, so a zero of a polynomial function, I'm calling the polynomial p of x, is the solution or the root of the equation p of x equals to 0. So the 0 means that if you evaluate the polynomial at that number, the output ends up being equal to 0. If you set p of x equal to 0 and solve the equation, you are finding the solutions to that polynomial equation, or another word for solution would be root, and the roots correspond to the zeros. Okay, the zeros of polynomial now in section 2.5 can be complex numbers because we're thinking inside the complex number system instead of like in 2.4 we were just thinking in terms of the real number system. Now we're in the complex numbers. And again, I've already said this, but we interpret zeros as x-intercepts only when the zeros are real numbers. So looking at this example here, so the function y equals to x squared minus 1 versus y equals to x squared plus 1. And just because you guys are familiar with translations and transformations, you know what those graphs look like. I put a sketch of them here, same shape. Just x squared minus 1 has x squared shifted down 1 unit, x squared plus 1 has the graph shifted up 1 unit. If I set x squared minus 1 equal to 0 and solve for the roots or the solutions to that equation, I could use square root method where I get x equals to plus or minus 1. Those are the real zeros, right? 1 and negative 1 are both real numbers. They're also technically complex numbers. They can be thought of like if you're being asked for all of the complex zeros, like you would list negative 1 and 1, or you could represent those as like negative 1 plus 0i and 1 plus 0i. But they're real zeros, meaning we can interpret them, or we know that those values end up corresponding to x-intercepts at negative 1, 0 and 1, 0. If we set y equal to 0 in this other equation, well, we get x squared equals to negative 1 and x equals to plus or minus the square root of negative 1, which you guys know simplifies to be plus or minus I. So I is not a real number. If there is an I, that can also be represented as 0 plus I or 0 minus I. So there are no real zeros or no real solutions to this equation. So the complex zeros are x equals to I and x equals to negative I. But there are no x-intercepts. Okay, so we could see in the graph on the left, or the function on the left, had 2 real zeros, right? These are real zeros, which corresponded to 2 x-intercepts. And then on the right, y equals to x squared plus 1, had 2 complex zeros, no real zeros though, and therefore no x-intercepts. All right, the fundamental theorem of algebra, this seems kind of like, well, duh, or just kind of a, why is this a theorem? But really it's the basis of all of the other theorems that we're going to be actually using, so it's very important. The fundamental theorem of algebra says that every polynomial p of x of degree n strictly greater than 0, so that means degree 1, 2, 3, 4, so on, has at least one 0 in the complex number system. Now that's the basis of the n-zeros theorem. And the n-zeros theorem is really helpful because it tells us that every polynomial can be expressed as a product of n linear factors in the complex number system. So, for example, a first degree polynomial, which is also a linear function, has exactly one linear factor. That makes sense. A quadratic function or a second degree polynomial could be expressed as 2 linear factors, a product of 2 linear factors. A third degree polynomial, or also known as a cubic function, could be represented as a product of 3 linear factors, and so on. So the n-zeros theorem tells us that p of x has exactly n zeros. However, this part's important, not necessarily distinct zeros. Remember, we can have zeros that have a multiplicity greater than 1, meaning repeated. If a 0 has a multiplicity greater than 1, it means it is a repeated 0. And therefore, you might have a factor that's raised to a power greater than 1, but each of those factors would still count as part of the n linear factors. Complex conjugate zeros theorem is going to be helpful for us as kind of like a shortcut almost for identifying the zeros of a polynomial function. So if a polynomial p of x has real coefficients, and if a plus bi is a 0 of p of x, then its complex conjugate, which would be a minus bi, is also a 0 of p of x. So to write this out in mathematical terms, if we have a polynomial function p of x, and we know that a plus bi is a 0, that means that x minus a plus bi is a factor of the polynomial. And if a plus bi is a 0 of the polynomial, its complex conjugate a minus bi is a 0, meaning x minus a minus bi is also a factor of the polynomial. And then there can be other factors as well. Now, notice that whenever you multiply this out, you're probably like, well, wait, if there's only real coefficients when this is multiplied out, what happens to the imaginary part of the zeros? Like, what happens to the I? Well, notice if we multiply these out, so if I distribute the negative, so I have x minus I minus bi times x minus a minus bi times x minus a plus bi, and I just, using distributive property to multiply that out, I would have x squared minus ax plus bi times x, and then minus ax plus a squared minus abi, and then minus bix plus abi, and then that would be negative b squared, but I times I is negative 1, so that would be plus b squared. Well, now notice what cancels. So bi times x minus bi times x cancels. Minus abi plus abi. So those cancel. Is there anything else that cancels? I don't think. So this ends up simplifying to be x squared minus 2ax plus a squared plus b squared. And this isn't you don't have to memorize anything for multiplying this out. My point in showing you this is that the fact when you multiply these factors out that have I in them, the i's end up canceling. Okay, so let's look at factoring this polynomial given that x minus 2i is a factor. Now, you could, to factor this, start by trying and listing all the possible rational zeros using rational root theorem, or rational zero theorem, also known as rational zero theorem. That would get you to a certain point. However, because you're given the fact that x minus 2i is a factor, which means that 2i is a zero of this polynomial, that tells you that you wouldn't be able to factor completely just using rational root theorem. So since we know that 2i is a zero, that means that its complex conjugate, sorry, let me silence that, negative 2i is also a zero. So because p of x is a fourth degree polynomial, that means that x minus, it can be rewritten as x minus 2i times x plus 2i, and then times two other linear factors or times a quadratic. So what we can do is we can actually multiply these two factors out and then divide the quadratic that we get from multiplying those out. We can divide that quadratic into our polynomial in order to figure out what this factor is. And then we can figure out how to factor that quadratic factor. Okay, so to multiply that out, I'm just going to think, I'm using distributive property, so x squared plus 2ix minus 2ix, and then negative 2i times 2i would be plus 4. Okay, so 2i times x minus 2i x, that cancels, so this multiplies to be x squared plus 4, and you might have been able to do that in your head. So I'm going to divide x squared plus 4 into p of x, so into the polynomial up here, in order to determine what times x squared plus 4 would give us that original, would give us our polynomial function p of x. Make sure that we are using placeholders in our polynomial long division. Okay, so we go what times x squared would give us x to the fourth, that's x squared. We multiply, so we get x to the fourth plus 0x cubed plus 4x squared, and we subtract. So minus 3x cubed plus 2x squared, and I'll bring the minus 12x down. And I go, okay, well, what times x squared would give me negative 3x cubed? That's going to be negative 3x. Distributing plus 0x squared, and then minus 12x. Okay, 2x squared, and then that will be plus 0x, and then bringing the 8 down. And I like to write the plus 0x as like a placeholder. Okay, so then plus 2, and then when I distribute that 2, we know that we should get a remainder of 0. Because we know that x squared plus 4 is a factor of p of x. We are given, by knowing that x minus 2i and x plus 2i are factors, we know that x squared plus 4, its product, would be a factor. So if you get a remainder here, something went wrong. Or if we got a remainder, we knew something went wrong. Okay, so x squared, this last factor is x squared minus 3x plus 2. Which, oh, that is factorable. Lovely. Okay, so that factors. So p of x can be written as x minus 2i times x plus 2i times x minus 1 times x minus 2. Because x squared minus 3x plus 2 factors to be x minus 1 times x minus 2. So we have factored p of x as far as we can. We have 4 linear factors that make up that product. So we can also see, even though the question is not asking for it, what all of the complex zeros are for this polynomial. Use another color. So I can list the complex zeros, which include the real zeros. Remember, real numbers are a subset of the complex numbers. So when I ask you for the complex zeros, you should be listing also the real zeros. So we have 2i, negative 2i, 1, and 2. So those are the complex zeros of this polynomial. Okay, so factoring this next polynomial, p of x, another quartic or 4th degree polynomial. This time, slightly different given information, right? We're given that 1 plus 2i is a 0 of that polynomial, which means that 1 minus 2i is also a 0 of the polynomial. So I know that p of x can be written as x minus 1 plus 2i times x minus 1 minus 2i times something. To figure out what that times something is, I want to multiply out those two factors and then divide into p of x again. So same sort of process that we did before. Now, there are 2 different ways you can think about multiplying this out. It's kind of a shortcut to rewrite it. So if I thought about distributing the negative, you're going to want to distribute the negative either way. So x minus 1 minus 2i times x minus 1 plus 2i. But if you, by the associative property of addition, group the x minus 1, notice that this factors to be like a minus b, or this looks like a minus b times a plus b, right? Which is what a difference of 2 squares factors to. So we can actually write this like a difference of 2 squares, or as a difference of 2 squares, as x minus 1 squared minus 2i squared, which x minus 1 times x minus 1, that's x squared minus 2x plus 1. And then 2i squared would be plus 4. plus 4? Because 2 squared would be 4. Sorry, that took me way too long. 2 squared would be 4. I squared would be -1. So this ends up being plus 4. And then just combining like terms, that's x squared minus 2x plus 5. Your other option is to not think of that as a difference of 2 squares factored and to just use distributive property and then have like terms, combine like terms, and the i's will cancel. Okay, so now I'm going to divide p of x by x squared minus 2x plus 5 to find what this remaining factor is. I'm going to give myself, I did not give myself enough room, so I'm going to add a page here in order to perform the polynomial long division. I'll stick with green. Have I been covering the microphone? Okay, so x squared times x squared will give me x to the 4th. Oh, I forgot to put my placeholder for the x cubed term. Okay, so that'll be minus 2x cubed plus 5x squared. Make sure you put those placeholders so everything works out nicely. So 2x cubed minus 7x squared. I'm going to bring the 16x down. And 2x times x squared would give me 2x cubed. Minus 4x squared plus 10x and subtract. So negative 3x squared plus 6x, bring the minus 15 down. And minus 3 times x squared gives us negative 3x squared. Again, make sure you don't have a remainder. Is that the same factor that we had before? No, it's just similar. Okay, so that factor, so p of x in factored form is x minus 1 plus 2i times x minus 1 minus 2i. And then x plus 2x minus 3 factors to be x plus 3 times x minus 1. So once your polynomial is in factored form, and we knew there were going to be 4 linear factors, we can also identify what the complex zeros are. Not asked for it here, but why not? So our complex zeros are 1 plus 2i, 1 minus 2i, negative 3, and positive 1. Okay, note, if the degree of a polynomial is odd, there's guaranteed to be at least one real zero. If the degree of the polynomial is even, there might not be any real zeros. This should make sense based on your knowledge of end behavior. An odd degree polynomial can either have end behavior like a line with a positive slope or a negative slope. So the graph is going to have to cross the x-axis at least one point. So that means there has to be at least one real zero. However, a polynomial that has an even degree has end behavior like a parabola that opens up or opens down. And therefore, everything can either happen above the x-axis or below. It doesn't have to cross the x-axis. Okay, so we want to just factor this polynomial. We don't have any other information. We're not given a complex zero or one of the factors, meaning to start with, you would be able to use grouping here, huh? But let's pretend we couldn't group. Let's use rational root theorem. So listing the possible rational zeros, leading coefficient is 1. The factors of the positive factors of the constant are 1 and 2. And then the leading coefficient is 1. So our possible rational zeros are plus or minus 1 or plus or minus 2. I'm going to check 1 first using synthetic division. Don't forget your placeholders for the x cubed term and x squared, the coefficients that are 0. If I bring 1 down, 1 times 1 is 1. 1 times 3, 3. 3. 3. Okay, our remainder is 0. Therefore, 1 is a 0 for this polynomial, or x minus 1 would be a factor. Okay, let's test negative 1. So if I bring 1 down, 1 times negative 1 is negative 1, add straight down. And what do you know? Negative 1 also works. So x plus 1 is also a factor. So there's going to be 3 more linear factors. Let's keep testing. Why don't we try negative 2? Okay, so negative 2 works, meaning x plus 2 is also a factor. Notice this represents x squared plus 1, which you guys know is a irreducible quadratic factor, or an irreducible quadratic. If we were to set x squared plus 1 equal to 0, right? Because this remaining factor right now is x squared plus 1. So factoring over the real numbers, that's done. But we're factoring over the complex numbers. Okay, we did this earlier. You get x equals to plus or minus I. Therefore, those remaining factors are x minus I and x plus I. So that's the polynomial factored over the complex number system, and our complex zeros are 1, negative 1, negative 2, I, negative I. Okay, and this one actually ends up working out similar to the other one, so I want to give you a different polynomial. so I'm going to change this. Here, I'll just write right over it. To be, P of x equals to 2x to the 5th minus 5x to the 4th plus 4x cubed minus 26x squared plus 50x minus 25, just to give us a little bit more of a challenge. We want to factor this completely and also identify all the complex zeros. Okay, so to start with, let's use rational root theorem. So factors of 25 are 1, 5, and 25. Factors of 2 are 1 and 2. So lots of possible rational zeros here, right? We have 1, 1/2, 5, 5/2, 25, and 25/2. So I'm going to start by checking positive 1 using synthetic division. Okay, bring 2 down, add straight down. Looky there, remainder of 0. So 1 is a 0, meaning x minus 1 is a factor. Now, I've already done this. You can use the strategy, and I use this strategy too, of checking to make sure there's not a repeated root, right? A repeated 0. So I'm going to test 1 again. The other strategy you could use is going through that entire list. So -1, positive, 1/2, -1/2, and so on. But I think it's maybe a good strategy to check again. And what do you know? 1 works again, meaning x minus 1 times x minus 1, or x minus 1 squared, is a factor of P of x. Okay. I'm going to next check 5/2. It just happened. 4 times 5 is 20, divided by 2 is 10. Okay, and then 25. Okay, so 5/2 also works. So what we know right now is that P of x can be written as x minus 1 squared times x minus 5/2. So that's 3 factors. And then times, what this tells us is 2x squared plus 4x plus 10. Now my suggestion is, once you get down to a quadratic, attempt guess and check. You can keep using synthetic division if you want, but you can either use guess and check. If guess and check doesn't work, then use quadratic formula. What I am seeing, and you do want to be careful because you're rewriting this polynomial in factored form. So you know that it's probably a good idea to factor out this 2, because if you were to just use quadratic formula, you would get the solutions to 2x squared plus 4x plus 10 equals to 0. However, you would lose the fact that the leading coefficient needs to be 2, because what you factor should also be able to be multiplied out and be equal to the original polynomial function here. So it would be a good idea to factor that 2 out. I see that that's not factorable. That quadratic is not factorable. So using quadratic formula, I'll use a different color for that. So x equals to negative b plus or minus the square root b squared minus 4ac over 2a. That's negative 2 plus or minus the square root of negative 16 over 2. So that simplifies to be negative 2 plus or minus 4i over 2, which is negative 1 plus or minus 2i. So P of x can be written as 2 times x minus 1 squared times x minus 5 halves times x minus negative 1 plus 2i. Oops, didn't need that extra parentheses there. Times x minus negative 1 minus 2i. And if you wanted to distribute that 2 into like the factor that's x minus 5 halves so that you don't have any fractions, so make that factor 2x minus 5, you could do that, or you can just leave the 2 factored out. So we can see that the complex zeros of this polynomial are 1, and 1 is repeated, right? Because it has a multiplicity of 2. So 1, which is repeated a repeated 0. 5 halves, negative 1 plus 2i, and negative 1 minus 2i.